Hello, everyone. Please take a seat. Thank you for spending your afternoon with us on scaling AI applications with Databricks, Hugging Face, and Pinecone. Please welcome to stage your speaker, Roy from Pinecone.
Hello, everybody. Thank you. I haven't even said anything yet, but so it's not needed yet. Okay, so today, we're going to talk about scaling AI applications with Databricks, Hugging Face, and Pinecone. And this talk is going to be basically broken into two main segments. The first, I'm going to basically give sort of an intro into how AI models think and kind of how vector databases work with in the larger context and ecosystem of AI applications. And then the second part is going to be more practical, where we're going to talk about the challenges, the motivations, and the challenges of actually scaling AI applications in practice. I'm going to go over an architecture of a scalable AI application, and then we'll just dive into some code, and then I'll hopefully have some time for Q&A. All right, so let's start by talking about how AI thinks. So obviously, AI doesn't think like we do. There are obviously huge differences, but there are also a lot of very interesting parallels, both mechanically speaking and almost philosophically speaking. So AI sort of mimics, and a lot of AI models do this, they sort of mimic the way that the human brain works. And they do that by using neural networks. And of course, again, these are all parallels, they're not exact facsimiles, right? But they're interesting to think about. So these neural networks are essentially a lot of artificial neurons that are arranged in layers, and they're interconnected. And the way these networks work is by being trained or exposed to huge amounts of data, and then these internal weights between these layers get adjusted over time. And then after this training process is completed, the neural network is capable of giving us predictions and giving us classifications, for example. And these internal features that are extracted from the data that the neural network is trained on, those are represented as vectors, which are basically long lists of numbers. And these vectors are also called embeddings. So what are these embeddings? These embeddings basically are an encapsulation of the relationships and the features that we can see from discrete objects that the network has been exposed to. So these objects could be words, they could be sentences, they could be documents, they could be images, audio files, and pretty much almost anything. And what happens within this model is that it basically transforms or projects data that lives in one space, for example, the semantic space, into the vector space. That's the nature of this term embedding. We're basically taking this data from one space and we embed it in another. And we'll see how that comes into play in just a minute here. So to sort of visualize this a little bit, as I said before, these vectors are high dimensional, right? That means that they're very, very, very long. And so this visualization that you see now is a really simplification of what actually is happening within the embedding space. It's much more nuanced and complicated than that, but this will help us kind of get an intuition into actually what's happening. So in here we have like these blue and yellow balls that represent embedding within this vector space. And what we can see here is that terms that are semantically related to one another are represented in this space as being closer to one another, geometrically speaking. And that's basically because what embedding models eventually let us do is apply mathematical utilities, like similarity metrics of all sorts, to basically extract the meaning and understand the meaning behind these embedded terms, these embedded objects. So meaning doesn't live in a vacuum. It's always contextualized. Meanings comes from the relationships between different things. And specifically, we can see in this example how a word, the word bank, for example, here, can have a completely different meaning depending on its context. So the three examples that we have here are, where's the Bank of England, where is the grassy bank, and how does a plane bank? And the sentence, the context, actually gives the word bank its actual meaning. And because these three sentences are different in their meaning, and essentially they give the word bank a different meaning each time, their embeddings are going to be dispersed and not close together within the embedding space. And conversely, when we have sentences that carry within them the same meaning, even though they don't use the same words, but rather they use synonyms, like, for example, the bees decided to have a mutiny against their queen, and the fine stinging insects rebelled in opposition to their matriarch, these two have the very, very similar meanings, and so they would be embedded. Their embeddings are going to live closer together in the embedding space. Okay, so now that we have a better understanding of what embeddings are, let's talk about vector databases and how they work within the larger context of AI applications. So a vector database, like the name suggests, is a database that stores vectors. And it's really good at querying vectors. It does that very, very efficiently. It was purpose-built for that exact purpose. Now, the way that generally vector databases work is that we create a vector, we store it, and then we provide the vector database with another vector, that is our query vector, and it would return to us a set of similar vectors based on some similarity metric that we can use. I'm not going to go into like which are the similarity metrics right now and how to choose them. We can talk about that offline if you'd like. But just know that like there are many ways of retrieving those similar vectors, and they mostly depend on how you created the embeddings in the first place. Another thing that vector databases let us do is they allow us to attach metadata to the embeddings that we create. And that comes in as a very useful thing when we build our AI applications, and later when I talk about the different use cases, you'll see why. Okay, so this is the general workflow that a lot of AI applications use when they are interacting with a vector database. So it usually starts with some set of content. So it could be a knowledge base, for example, of a bunch of documents, for example. That knowledge base, that content is going to be passed to an embedding model, which is, again, is an AI model where we're not asking for a classification. We're just asking for the model's internal representation of whatever we're giving it. Those vector embeddings are then going to be saved in the vector database together with some metadata that usually originates with the content that we create the embeddings from in the first place. And then when the application wants to interact with the vector database, the application will send its query and again embed it using the same embedding model that the content was using to be embedded with, and send that vector embedding to the vector database and eventually get the results back in the form of similar vectors with their associated metadata. So how do vector databases fit in the world of AI applications? So the strength and the weakness of AI models lies in the fact that they are essentially black boxes, right? We can get results from them, but they don't really tell us why those results are the way that they are. And so vector databases sort of flip the script a little bit, and they allow us to sort of peer into the inner workings of these AI models. And the way that they do that is, number one, we're now not asking for an inference from our model. We're taking those embeddings, those inferences, as the one step before the actual inference, the actual classification, and we're storing it directly in our database. And now we can interact with it and start making sense of those embeddings and understand how those internal representations actually work and how like different terms and different objects within that embedding space are laid out. And that is the way that we can start making sense of the internal build, the way that these models are built internally. And the second way that vector databases allow us to sort of better use AI models and kind of break that black box is, again, by allowing us to associate those embeddings with metadata. And now we're not just reliant on whatever the model just gave us. We have this association that we've created between the internal representation of the model and some structured data that is trusted by us, that we have created and we have associated with that embedding. And I'll show how that works in practice in a minute. So there are many, many use cases for vector. I'll take questions in the end if you don't mind. There are many, many use cases for vector databases. They run the gamut from semantic text search through recommenders, image search. There are many anomaly and fraud detection use cases, but I'm going to talk specifically about 3 of these use cases today. So the first is semantic search. Semantic search is perhaps the most common use case that we see for vector databases today. Basically, we have, again, a knowledge base. We want the ability to allow the user to interact and ask the knowledge base queries that are not reliant on just keywords, but actually understand the meaning, the intent, and the context that the user is coming with. And vector databases, again, because of this ability to leverage these embeddings, they allow us to do exactly that. For that reason, they also are really good at dealing with ambiguous terms and long-tail terms as well. And we're not limited to only using semantic search in a vacuum. We can also combine it with more traditional methods like BM25, which have been used to create keyword search before, and that is called hybrid search. Another common use case for vector databases is image search. So vector databases don't care about the origins of the embeddings that are stored within it. So if you create an embeddings from text, you can store it in a vector database. If you create an embedding from an image, you can store that too. And the mechanics are exactly the same. You first embed whatever it is, the piece of content, image or audio or whatever it is, and then you can query the vector database based on that embedding. And so we can see a lot of different use cases for that, from product search through agriculture, disease detection systems, and a lot of different other use cases as well. The last use case I want to talk about today is generative AI, and specifically LLMs. So as we all know, generative AI and LLMs specifically are really good at generating content given some prompt. These LLMs are really good at basically predicting the next word given all of the data that they've been trained on and whatever data they got within a given session or within a given context. That is both a good and a bad thing, right? So these LLMs they could be very general because the data that they've been trained on could have been the entire internet. But at the same time, that's also a limiting factor because their ability to answer reliably in a domain-specific field where we have special terms that aren't used in a general sense, they're going to have a harder time. And one of the biggest problems is that they don't tell us that they don't know. They basically give us an answer and hallucinate. And basically their answers could be completely disconnected from reality. And so how can vector databases help with this issue? So it's twofold. Number one is vector databases can introduce a semantically relevant knowledge to the LLM. And again, we do that by taking our domain-specific knowledge base, for example. So let's imagine I'm working in finance and in a bank, and there are many, many terms that are only relevant to me. I can take the documents for my company, for my bank, and index them, and create the embeddings for them and index them. And now I can start using combine the use of the vector database and the LLM together by using what's called retrieval augmentation generation. So retrieval augmentation generation is basically this concept of, again, we take the knowledge base, we take the prompt that the user started their interaction with the LLM with, we embed that as well, we retrieve semantically relevant content, and then we inject that content into the context window of the LLM. And now using prompt engineering, we can focus the LLM and tell it, hey, answer my questions only based on the context that I've just given you. And that, in a lot of cases, reduces the chances that the LLM is going to hallucinate, and it increases the chances that it's going to use semantically relevant content, right, on the one hand. And on the other hand, because we are able to associate metadata and structured data with our embeddings that are, again, the part of what comes back as a result of any query to the vector database, now we are able to ask for actual sources, right, that we can point to. They could be documents, they could be URLs, and so on and so forth. And now the answer that we would get from the LLM is grounded in something that we can trust, in something that we can explain. Okay, so that's kind of like the first part of the talk where I gave some kind of an understanding of what embeddings are, what vector databases are, and kind of how they all fit together. And now we'll start talking about this issue of scaling, because the main impetus for wanting to scale these operations is basically very simple. The more embeddings you have, the more accurate your application is going to be, and more reliable your application is going to be. And that doesn't matter if you're building a semantic search engine, an image search engine, a recommender, a fraud detector. You need as many embeddings as you can put your hand on, right? And that is a challenge because it's easy to start with small systems that kind of handle hundreds of thousands and millions of embeddings. It's harder when you're at the scale of hundreds of millions and maybe billions of embeddings. So why is this so hard? First reason is generating embeddings is a very compute-intensive task, right? In most cases, you need to use a GPU if you want to do it efficiently, right? And that is not an easy thing to accomplish, definitely not at scale. In many enterprise scenarios, in those scenarios that usually ask for that scale, we can't use third-party model providers, right? So we can't just go to OpenAI and say, hey, let's take all of our data and send it over the wire. We actually have to maintain some control over it, and that is a challenge in and of itself. So we need to be able to take a model and apply it also at scale. Then, like with any other big data problem, we need to sanitize our data. We need to make sure that we make our processes continuous as possible, so use streaming whenever possible, just to make the whole process more efficient. We will eventually need a place to store the embeddings that we are creating. And again, we'll have to do that in a place that is capable of scaling up to hundreds of millions of billions of embeddings and not take a hit when you're actually querying those embeddings later on. Whenever this data doesn't just get stored and then dies, in most cases, in almost all cases, we have to update these embeddings, and we have to do that quickly in order to make sure that our data is as fresh as possible. All that to say that traditional solutions for all of these problems are probably not the way to go, and we kind of need to rethink and sort of think of an architecture that will fit this type of problem. So that leads me to kind of the more meaty part of this talk, which is, okay, so what do we do? So the basic solution that we've been seeing a lot and we've been using ourselves is combining Databricks, Hugging Face, and Pinecone. Databricks is basically responsible for all the pre-processing and the embedding process. Hugging Face is going to provide us with a lot of models to use that are open source. Pinecone is going to store our embeddings and then serve them downstream. And I'll go into the details of how exactly that works. So I'll talk a little bit about each one of these components. So Databricks and the data lake is like a well-known system that allows us to build these pipelines at scale. It's also important to mention that it's not a hard task, right? And you'll see that in the code. The way we put these pipelines together is incredibly, incredibly simple. They allow us to understand where this data comes from and where it's going. So I'll show that as well. We have this very nice lineage graph that shows us how the data pipeline is constructed. It's very well, it scales very well for even the biggest data sets. So we've tested this with millions and tens of millions of embeddings and with small clusters, and it performs pretty well. And of course, it allows us to work on these projects collaboratively. And if anyone here that's used Databricks notebooks knows exactly what I'm talking about. HuggingFace is one of the biggest sources for open source AI models and data sets that we can start playing with. They allow us to create our own versions of these models and data sets and version control them within HuggingFace, which comes in to be very useful when we're developing these models. And then finally, they allow us to set up very easily inference endpoints that allow us to test these models before we attempt to use them in a larger scale. And then finally, Pinecone. So Pinecone is a fully managed and distributed vector database. It allows us to create and manage and scale indices in using a very, very easy API or using a UI console. Pinecone can handle hundreds of millions and billions of vectors, like I mentioned before, all the while maintaining very, very low latency and optimized for cost and performance. So putting all of these together, we'll use Databricks, like I said, to parallelize this compute effort that we need to basically clean the documents and sanitize the data, to then create the embeddings as well. We'll do that in Databricks using the HuggingFace model. We'll do this continuous processing using Delta Live tables, which is a wonderful, wonderful tool. We'll store all of these embeddings in Pinecone, and then we'll also perform ongoing updates using the Pinecone connector, which handles these writes very efficiently, even at large scales. So this is what the overall architecture of a solution like this looks like. So we start with some raw data store, right? That could be a Hive metadata, a Hive store, or really anything, an S3 bucket, it really doesn't matter. We then use Delta Live tables to read that data and turn it into a stream. It goes through this process of data sanitization and segmentation. So for example, in the example that you'll see in a moment, we have documents, and we don't want to process the documents as a whole, but we rather want to segment them by sentence. So we do that in Delta Live tables as well. We then call in the HuggingFace embedding model and create the embeddings using DLT as well. These generated embeddings are saved in a Hive table after they're generated. And then we use the Pinecone connector to write those from the Hive table into Pinecone. And then down the line, applications can consume that, consume those embeddings by interacting with Pinecone's API. Okay, let's move on to some code. Okay, can everybody see this? Yes? Okay, cool. So there's not a lot going on here in this first cell. There's like a whole bunch of installation of required packages that I won't go into, and then a bunch of imports. But this is where things start getting a little bit interesting. So like I said, we're starting by reading the data that we're going to ingest from a Hive table and convert that into a stream. Okay? Then we take that stream, and in this case, I'm doing some kind of operation that just helps us with cleaning up data that we don't need. So I'm generating UUIDs for each document that I'm reading, and I'm dropping a column called summary that I'm not interested in. So you can think of this step as being your data sanitization step, where you could probably handle any issue that you have with the data set that you're starting with. This is the segmentation step. So here I'm basically creating a new column where I'm taking the document and I'm running an explode function on that document, and I'm generating a new ID where I have this association between the document, so that I can have an association between the original document and the sentence that has been included in that document. Okay, so I'm going to want to be able to refer back to that document when I retrieve the results back from the vector database. This UDF basically does all the work of creating the embeddings. So as you can see, I'm basically specifying the model that I want to use from Hugging Face. So this essentially could be any model that you want that can provide embeddings, and not all of them can provide embeddings, but a lot of them can. And this is the way that you basically specify the model that is going to be used to generate the embedding. We then call this model over here for every sentence that I have. So I'm going to get a series of sentences into my function. And I'm going to get here, and this is exactly where the embeddings are being calculated, right here. And then I return these embeddings as a list. So again, all I get back is a list of numbers, right? This last step is basically taking the original document DLT table and running the function, this create embedding with transformers, on the sentences. And then I'm also adding some metadata. Like I mentioned, we need some metadata. So I'm creating this JSON structure that is going to tell me for each embedding what is the original document ID that I got that embedding for. And again, imagine this could be a URL, this could be any piece of information that's going to help me understand what is the relevance and what is associated with the embedding that I've created downstream. So that's all that it takes to create this pipeline. What it looks in practice when we look at the pipeline after it's run is we get this nice graph where we're going from the raw stream through the documents to the sentences, and then finally to the embeddings. When that process is complete, we can use the Pinecone connector to read from a table where these embeddings were written into, and we write it directly. We take the data frame and we write it directly into Pinecone. Unfortunately, that doesn't work with streaming at the moment, but it will hopefully in the near future. But for now, this works in batch mode. And that's all. I'm very eager to hear your questions. If you have any, please.